Now, let's imagine it would take billions of years to create a galaxy like the Milky Way, with over 100 billion stars throughout billions of years. However, the James Webb Space Telescope has identified hundreds of ancient galaxies existing at the birth of the universe. Some of these galaxies have shapes resembling a magnified copy of the Milky Way, 10 times larger when the universe was just over 500 million years old. In an ongoing effort to unravel the mysteries of the universe, humanity has embarked on a quest that transcends time itself. We are on a mission to find answers to age-old questions woven into the inferences and indirect evidence of scientists. Ancient galaxies with ages surpassing that of the universe itself. This revelation raises more questions than it provides answers. How can a structure be older than our universe? Does the Big Bang Theory have inaccuracies in explaining the uniqueness of this universe? The pursuit of understanding the universe will take us deeper into the unknown, opening doors to mysteries that challenge the very foundations of our understanding. HHD 10283, the star that existed before the formation of the universe. The story begins with an ancient star located more than 200 light-years away from Earth. As the dawn of the universe unfolds, it nestles itself near the constellation Libra, with an apparent magnitude of about 7.205. This star first came to attention in 1912 when Walter Sidney Adams measured its astrophysical properties using a spectrograph at the Mount Wilson Observatory. Since HD 10283 does not belong to the main sequence, and is not a red giant, its initial position on the Hertzsprung-Russell diagram was explained through data and theoretical models of stellar evolution based on quantum mechanics and observations of millions of stars. In the year 2000, utilizing data from the European Space Agency's Hipparcos satellite, astronomers calculated that the star HD 10283 has an estimated lifespan of up to 16 billion years. This posed a significant challenge for astronomers, as the calculated age of the universe based on microwave background radiation is 13.8 billion years. This conundrum is known as the age paradox in astronomy. Perhaps due to the extraordinary nature of HD 10283, scientists have given it another name, Methuselah, after the biblical figure who lived to be 969 years old. Structurally, Methuselah is a gaseous sphere with two main components, hydrogen and helium. This aligns with its birth circumstances. Around 500 million years ago, when the first generation of stars formed, iron was still a rare element in the universe. However, the debate here isn't about that. The puzzling question is why Methuselah could exist for more than 2 billion years longer than the entire universe. Astronomer Howard Bond of Penn State University and his research team delved deeper into this issue. They scrutinized data collected by the Hubble Space Telescope from 2003 to 2011, recording the positions, distances, and energies of numerous stars. By cross-checking various scientific measurements, they hoped to pinpoint Methuselah's age more accurately. Scientists believe there must be some subjective factor that led to inaccuracies in the calculations, likely stemming from errors in precisely measuring the star's distance. Conventional measurements allow them to use the star's distance and apparent brightness to calculate its actual brightness and estimate the star's age. The brighter the actual brightness, the younger the star. Distances to stars are measured using parallax, the slight shift in the position of observed stars over 6 months when Earth is at opposite ends of its orbit. The second cause contributing to age miscalculation comes from the theoretical model of the star, such as the accuracy of nuclear reactions in the core and the diffusion into the interior of various elements in the star's outer layers. Bond's team suggests that helium in the outer layers of the star diffuses more deeply into the core than previously estimated. As a result, nuclear fusion reactions may burn less hydrogen than predicted, indicating that this star might be younger than initially thought. The third reason is attributed to the abundance of oxygen. The ratio of oxygen and iron in Methuselah might be higher than predicted. In the first few million years after the formation of the universe, oxygen was also a rare element, potentially implying that Methuselah is younger than previously estimated. After numerous observations and analyses, Bond's research team finally estimated the star's age to be 14.46 billion years, significantly reducing it from the initial figure of 16 billion years. However, with this estimate, HD 2283 is still older than the universe. Nevertheless, this estimate could have an error of about 800 million years, and Bond believes this doesn't contradict the evolutionary history of the universe. Bond's team then published a more in-depth study in 2014, narrowing down Methuselah's age to 14.27 billion, plus or minus 700 to 800 million years. However, Robert Matthews, a physicist at Aston University in Birmingham, United Kingdom, felt that the star's issue wasn't as simple as it seemed. In fact, in July 2019, at the International Conference of Astrophysicists in Santa Barbara, California, USA, the question of how old the universe is once again arose. Astronomers, including 2011 Nobel laureate Adam Rees, when observing galaxies relatively close to us, discovered that the universe might be younger by hundreds of millions of years than the predictions based on microwave background radiation. The concept of the universe's age stems from the phenomenon of cosmic expansion, and this new research indicates that the universe is expanding about 10% faster than previously estimated. In 2013, through observations of the cosmic microwave background radiation by the European Space Agency's Planck telescope, scientists calculated the age of the universe to be 13.8 billion years, with an expansion rate of 67.4 kilometers per megaparsec. However, recent measurements indicate that this value is closer to 74 kilometers per megaparsec. This means that current measurements of the universe's expansion rate do not align with predictions based on the physics of the early universe. With an expansion rate of 74 kilometers per megaparsec, the corresponding age of the universe would be around 12.7 billion years. After 2019, the latest estimates, even reported by the New York Times, have raised this constant to as high as 82.4, suggesting a universe with a corresponding age of 11.4 billion years. Therefore, the question of Methuselah's actual age remains unresolved. Matthews believes that astrophysicists might be misunderstanding the issue, not due to negligence, but because the observations and theories required to estimate the age of the universe are more complex than those for individual stars. He thinks that there are two sources of errors in estimating the age of the universe. One is the presence of observation errors not fully understood, and the other is errors in the model of the universe's evolution. According to the history of science, the truth often lies in both. Matthews suggests that dark energy might vary over time, a possibility proposed by physicists before, indicating that this could align with the causal set theory in quantum gravity. The actual age of the universe. In cosmology and astronomy, nothing can be considered a conclusion. The clearest evidence for this is the quest for the true age of the universe by humanity. Scientists suggest that the age of the universe can be determined by analyzing light and various types of radiation traveling from distant space. But they do not always agree on the age of the universe and continue to seek more accurate answers with each improvement in space observation telescopes. In the 1920s, astronomer Edwin Hubble discovered a way to determine the relationship between the distance of an object based on the time it takes for light to travel from that object to Earth, and the speed at which that light is moving away from Earth, based on how much light from distant locations has shifted to redshift phenomenon, where light emitted from objects moving away from the observer appears redder. This figure is now known as the Hubble constant, describing the expansion of the universe at different locations. According to NASA, the Hubble constant is higher for objects farther away, and vice versa. This indicates that the universe's expansion is accelerating, making the calculation of the universe's age more challenging. Currently, many scientists believe the universe to be 13.8 billion years old. They derived this number based on calculations in 2020 after re-evaluating data provided by the European Space Agency's Planck spacecraft and analyzing data collected from the Atacama Observatory in Chile. Using this calculation, the universe is approximately 100 million years older than previously estimated, based on the data Planck provided in 2013. Both the Planck spacecraft and the Atacama Observatory have mapped the cosmic microwave background, CMB, the light remaining from the Big Bang explosion. By combining this data with existing models of the rates of emergence of various types of matter and celestial bodies after everything began, scientists can estimate the time frame of the cosmic birth explosion. According to scientists, light from the cosmic microwave background, CMB, appeared around 400,000 years after the Big Bang. The universe began in a state of plasma, where photons, or light, were bound to electrons. Eventually, the universe cooled enough for photons to separate from electrons, leave the plasma, and wander freely throughout space, forming the CMB. By measuring the scattered light from the CMB at various distances, scientists can estimate the age of the universe. The figure of 13.8 billion years was provided by a group of scientists at the Flatiron Institute's Center for Computational Astrophysics in New York, USA in 2020. The research team re-examined the CMB using observations from the Atacama Observatory. Dr. Simona Ayola, the lead researcher, mentioned that although the Atacama maps covered a smaller area compared to the Planck spacecraft maps, the higher resolution allowed for more precise measurements. Dr. Ayola and colleagues made a breakthrough by observing the CMB at the smallest scale to date. This allowed them to see more details and anomalies, providing insights into what happened in the early universe and when. By comparing these high-precision maps with predictions about the age of the universe, the research team calculated the age of the universe to be 13.8 billion years. Could the universe be even older? It's a possibility. As telescopes continue to improve, becoming more modern, they have the potential to peer further into the past than we can currently imagine, revealing something that might change our entire understanding. The universe expands. Regarding the issue of uncertainties in the evolutionary model of the universe, new theories related to dark matter, dark energy, or the acceleration of cosmic expansion are currently under the scientific community's scrutiny and explanation. The conclusion about the accelerating expansion of the universe, based on the analysis of type Ia supernovae, the spectacular explosions of dead stars, recorded by the Hubble Space Telescope and numerous other large ground-based telescopes, led to the widespread acceptance of the idea that the universe is dominated by a mysterious entity called dark energy, causing accelerated expansion. Now, a group of scientists led by Professor Subir Sarkar from the University of Oxford has raised questions about this fundamental proposition of cosmology. Using massive data, a catalog of 740 type Ia supernovae, which is 10 times the number used in previous studies, researchers found evidence suggesting that the acceleration may not be as clear as previously thought. The data indicates that the rate of cosmic expansion remains constant. Professor Sarkar, who also holds a position at the Niels Bohr Institute in Copenhagen, believes that the discovery of the accelerated expansion of the universe has garnered the Nobel Prize, the Gruber Cosmology Prize, and the Breakthrough Prize in Fundamental Physics. It led to widespread acceptance that the universe is dominated by dark energy. However, there is now a much larger dataset of supernovae for rigorous analysis and statistics. Scientists analyzed the latest catalog containing 740 supernovae, more than 10 times the sample size used in previous breakthrough discoveries. Through this, they found evidence that the accelerated expansion is not quite reaching the standard required to confirm a fundamental study. Other data support the idea of accelerated expansion in the universe, such as information about the cosmic microwave background, CMB, obtained from the Planck satellite. All these experiments are indirect, conducted within the framework of an assumed model, and the CMB does not directly experience the impact of dark energy. Therefore, it is possible that we have made a mistake, and the existence of dark energy is just a consequence of analyzing a too simplistic theoretical model built in the 1930s, long before real data became available. A more complex theoretical framework lies in observations suggesting that the universe may be inhomogeneous and that its matter does not behave like an ideal gas. Two fundamental assumptions of cosmology. This could explain all observations without the need for dark energy. Indeed, vacuum energy is something we understand very little about in terms of fundamental theory. Naturally, much more research would be needed to convince the physics community of this, but Sarkar's group's research serves to demonstrate the instability of a pillar of physics. The researchers also found that, although the universe's expansion has been accelerating for billions of years, the driving force of dark energy may be diminishing. According to their model, the universe's acceleration could rapidly cease within the next 65 million years, after which, within 100 million years, the universe might stop expanding entirely and instead enter an era of contraction, which could be either a death or a rebirth of time and space. Dark matter and dark energy. Another issue complicating the determination of the true age of the universe is dark matter and dark energy. It seems that the capabilities of current models and theories in explaining observations and evidence have reached their limits. From the microscale of atomic particles to the macro scale of the cosmic extent, contradictions arise at every turn. Before the issue of the universe's accelerated expansion became a fiercely debated topic, leading to the rebranding of the cosmological constant as dark energy. The mass of matter in the standard cosmological model also posed a heap of intricate problems. The term dark matter is now commonly used to describe that missing mass. To account for this, scientists began searching for heavy, weakly interacting particles, a type of matter challenging to observe or detect, but possessing strong gravitational effects. So far, potential candidates continue to elude discovery, and no standard cosmological theory indicates where this massive dark matter might currently be hiding. Continuing with the list of prominent issues is dark energy. Although it shares a name resemblance with dark matter, the two are fundamentally different. Dark energy is related to the problem of the expanding universe and contributes to explaining why seemingly illogical stars like Methuselah continue to be discovered. In the late 1990s, observations of more distant celestial bodies indicated not only that all galaxies were moving farther apart, but also that the rate of this expansion was increasing. It appears that galaxies are accelerating away from each other. In physics, acceleration is known to occur only when a force is acting. Therefore, the accelerated expansion of galaxies implies the existence of a force opposing and surpassing the gravitational force, causing matter to accelerate away in all directions. Initially, Einstein introduced this idea along with his famous cosmological constant, essentially an arbitrary number added to his equations to create a universe in a state of equilibrium and stable balance, rather than collapsing under its gravitational pull. Einstein later admitted this to be a mere ad hoc move, with no experimental evidence or theoretical substantiation, describing the cosmological constant as the biggest blunder of his life. However, with the latest observations, the cosmological constant has been reintroduced as dark energy, energy associated with space acting to push matter apart. Yet again, this is not a small discrepancy. The latest calculations indicate that dark energy may account for 73% of all mass energy in the universe. Dark matter contributes the next 22%. leaving only 5% for actual physical matter and radiation that we can detect based on observations. Nevertheless, there is no shortage of legitimate explanations for these issues from the scientific community. Friedrich Engels, alongside Marx, was one of the founders of scientific socialism, and when arguing against scientists who were content to attach the word force as an explanation to cover up gaps in their knowledge, Engels remarked, "Sometimes we seek refuge in the word force, not because we fully understand the laws, but precisely because we don't understand those laws, because we haven't seen the rather complex conditions of those phenomena. Big Bang is right or wrong." After being subjected to numerous revelations by James Webb, and with lingering gaps in the physical arguments, the Big Bang theory finds itself on the public grill once again. The issue extends even more fundamentally to the relationship with the standard model for cosmology according to the Big Bang, particularly concerning the Big Bang itself. The primary evidence for the Big Bang theory, an event in space and time when all matter in the universe was concentrated at a point, is contradicted by observations showing celestial objects, such as galaxies, moving apart, implying a common point from which that motion originated. The concept of a Big Bang, related to a point where all matter concentrates, known as the singularity, poses a massive problem for cosmologists that remains unresolved. First, in the theoretical singularity, the density of matter must be infinite, and at that point, all known laws of physics cease to operate. Second, the problem arises, where does the energy for that Big Bang come from? Some argue that the Big Bang, and consequently the formation of the universe, simply arose from a quantum fluctuation, meaning a random excitation in space-time. However, if nothing existed before the Big Bang, no matter, no energy, no motion, no space, and no time, how can the laws of physics, including quantum mechanics, exist or have any meaning? The quantum fluctuation of what, from what, and within what? Ultimately, and more crucially, concerning the remarks made earlier, what existed before the Big Bang? Some propose the hypothesis that that moment was the point of creation for the entire universe, the origin of all motion, a first push. So, what was there before? Some modern theories suggest the existence of a universe containing matter in an absolute static state, a universe without motion. Then, what makes the universe move? What force, outside the universe, could provide the transition from a static to a dynamic state? As Engels explained in his anti-Düring polemic, when proposing a leap from the static to the dynamic, one ultimately has to invoke a supreme being. If the world has ever been unchanging, then how could it transition from that state to the changes observed? An unchanging state, furthermore, has persisted since ancient times, so it cannot spontaneously escape that state, undergo motion, and experience changes. Thus, there must be an initial push from outside, from beyond the world, to set it in motion. But everyone knows that the initial push is just another way of referring to a supreme being. The idea is that instead of a leap from a static state to a dynamic state, perhaps nothing existed at all, and then something, that is, the creation of the entire universe from nothing, including all matter and energy, would be just as illogical and ultimately the same. Motion is the existence of matter. Anywhere and at any time, there can be no matter without motion. No matter without motion, as well as motion without matter, is inconceivable. Therefore, motion is neither creatable nor destructible, just like matter itself. The amount of motion existing in the world always remains the same. Thus, motion cannot be created, but only transmitted. From nothing, inaccurately, only nothing can arise. This is a fundamental principle of physics and dialectical materialism. It is reflected in the scientific law of the conservation of energy. Energy is neither created nor destroyed. Talking about the beginning of time, therefore, is entirely meaningless. Yet that, the mysterious creation of something out of nothing, is the prevailing paradigm in the current model of the Standard Model of Big Bang Cosmology, SMBBC. Thank you for accompanying us on the adventurous journey to the distant corners of the universe through the sophisticated eyes of the JWST telescope. The images of ancient galaxies unfolded before us like windows to the past, allowing us to revisit the origins of the universe and witness new heights in science. Remember, these discoveries are not just numbers and images on paper. They are keys to unlocking the grandest mysteries of nature. We are gradually unraveling profound questions about our existence in this universe and its formation, bit by bit. If you found it as fascinating and awe-inspiring as we did, don't forget to like, share, and subscribe to the channel to continue with us on the next scientific adventures. Thank you for being a part, and we'll meet again in the upcoming journeys. Farewell and keep fueling your passion for the universe.